Now we'll discuss second problem. Say problem is given, draw SFD and BMD of simply supported beam subjected to a moment M at its center C. Right? For this given loading diagram, we have to make a shear force diagram and bending moment diagram. Now follow this step that we have discussed earlier. First we will find the value of each load point here. Reaction RA and RB are known, so we will go through the static equation to calculate reaction. Sigma Fy equal to 0 if we consider, then RA plus RB equal to 0 because there is no external vertical force acting on this beam. Or we can write RA equal to minus RB. Now take moment about B. Sigma MB equal to 0. Length of beam is given L. In this case, moment about B is RA into B, RA into L, and this external moment given M, it is in clockwise direction, and for calculation of reaction we follow the simple convention of moment. Either we can consider clockwise moment positive or anti-clockwise negative. Similarly, anti-clockwise positive or clockwise negative. So here we are considering clockwise positive. So RA into L, it is rotating the beam in clockwise direction, and next is M, complete this arrow, it will form a clockwise rotation. The moment is given M, RA into L plus M equal to 0. So here RA equal to minus M by L. So RB will be RB equal to, this is minus of RA, it is M by L. So load at each point of the beam is known now. This is of equal to minus M by L and this is equal to plus M by L. Now calculate shear force. For the section AC, shear force for section AC. Here C, if we C is not a load point, here moment is given. So basically there are two load points A and B, right? But external moment is given. So in case of bending moment analysis, we will consider this C as a load point. But in case of shear force analysis, because in case of shear force, we consider only the external vertical forces acting on the beam. So at C, there is no vertical force acting on it. So there is only one segment from A to B, right? So we can take a section just left of B, just left of B from moving from left to right hand. So Fx equal to here minus M by L, because we are taking section, there is one section for this case, here we will consider section and this will be our x length, right? The Fx equal to M by L. For x equal to 0, there will be point A, and for x equal to L, there will be point B, but this expression is independent of x. So directly we can write Fa equal to Fb equal to minus M by L, and this equation is quite similar to y equal to minus C, that is the equation of line parallel to x-axis on a distance M by L on negative y axis, right? So this is equation of parallel line constant line. So now we can draw shear force diagram for this values, because there is only one segment and FA and FB is known and variation is constant line. So this is point A, value at A is minus m by L, this is m by L, right, and value at B is minus m by L, and variation is constant line. Draw a constant line. Now close the curve. This is our length L. This is point B and this is point A. This is your shear force diagram. Now for the same section, now we will calculate bending moment. First consider section AC. Here we will divide the beam in two parts, because in case of bending moment we have to see the moment at each load point. We have to observe moment for each load point, right? So A, C and B, because at C there is a moment, so C will be a load point. So first we will consider segment AC, right? To consider a section, just left of C and distance is x. For this x length of beam, when we write the equation, it will be mx equal to minus m by L into, plus minus m by L into x. Observe this minus m by L, this is in upward forces. Upward moment of upward force for left segment is positive. We can consider positive. This minus m by L is magnitude, right? This is magnitude. Don't consider it as it is negative. So minus m by L into x. There is no other force, so moment remains same, minus m by L x, right? So for the value point, now mx, then when x equal to 0, there will be point A, MA equal to 0, and for x equal to L by 2, MC equal to, question is mx equal to minus m by Lx, so it can be written as m minus m by L into L by 2. So this is minus m by 2, because L cancel out, right? So MC equal to minus m by 2. Now we can draw. Now go for the second segment. Segment is now CB. CB. For this segment, now section is this one, just left of B, and distance of this segment from B is C is x, right? So when we are considering, we will make a loading diagram of the segment here. This is point C, here is a moment M, and here is the segment. This distance is x, this is RA equal to minus M by L, right? And this is length L by 2. Now length of analysis for bending moment is L by 2 plus x. For this segment we will calculate bending moment value, right? So mx equal to, now Ra into L by 2 plus x, we will take the moment of Ra about this cross section. So this is minus m by L into L by 2 plus x, and this moment is now, we will consider this whole moment. Before this equations we have not considered it, right? Because we are considering just left of C, so we have ignored the effect of this external moment, and after this point we are considering it. So this is clockwise moment. For the left segment we have considered the upward moment of upward forces is positive or clockwise moment is positive, because upward forces causing the rotation of beam about this cross section in clockwise direction, and this rotation is given in clockwise direction, so it is positive. For x equal to 0 there will be point C, and for x equal to L by 2 there will be point B. So for x equal to 0, mc minus m by L, L by 2 plus 0 plus m. So here it will be minus m by 2 plus m, or either will be equal to capital M by and 2. And for x equal to L by 2, it will be point MB, and from the calculation we will find that it will be equal to 0. Why? When we will solve this problem from right in to left in, then B will be the first point and there is no external moment given. So moment about this point will be 0. Already we have discussed in problem 1. So moment at each load point is now known. So we can draw the bending moment diagram for this case. Here is the length of beam. This is point A. At point A, the value is 0. At point C, the value is minus m by 2. This is point C. M by 2 minus m by 2. So it will be below the reference line. And variation, here x ki power 1, here the x ki power 1, so this is like equation of y equal to m into c. So it is showing a linear relation, y equal to m into c inclined line equations. So at C, for the position AC, the variation of shear force is plotted. This is point A and this is point C. Now come to the position CB. For the position CB, the bending moment value at point C is positive m by 2. Here it is positive m by 2. And for point B it is 0. And again here is x ki power 1. Here x to the power 1. So variation relation between mx and position of cross section is of linear nature. So again there will be an inclined line in between them from C to B, and it is the rule of graph when there are two values just above and below, then they will be joined by a straight line. So this is the bending moment diagram for the problem 2, right? Now consider the case now discuss problem 3. Draw SFD and BMD for simply supported beam subjected to UDL of small w Newton per meter along its length, along its entire length, right? First, we will draw the loading diagram. For this case, loading diagram is, this is a simply supported beam A and B. Here is a reaction RB, RA, and it is subjected to uniformly distributed load of small w Newton per meter, right? Now, first step is to find out the reaction. When we will draw the BD of this diagram, then there will be total weight of UDL at its center, it is of magnitude WL, work out at distance L by 2 of the beam. When it is at the center of the beam, then reaction will be just half of this total load, RA equal to WL by 2 and RB equal to WL by 2. Now we will calculate CFO's value for the beam. There are two load points A and B, so there will be only one segment, right? Now we are moving from left to right and segment is AB. So section will be just left of B. Length for analysis is X. Write the equation for this X length of beam. If we draw the loading diagram for this section, it will be like this one. Here is WL by 2 and distance is X. Now Fx equal to, for this length, Fx equal to WL by 2, intensity of this UDL is W Newton meter. The Fx equal to will be WL by 2 minus W into X. Why we are taking here W into X? Because this UDL also come on its X length of beam, and the magnitude of total weight of this UDL for this X length of beam will be W into X, and it acts in downward direction, so it is negative, right? For now, this is the CFO's value for this section, for section AB. Now we will calculate the CFO's value for each point lying under this section. For x equal to 0, there will be point A, FA equal to W L by 2, and this term will be 0, so FA equal to W L by 2. For x equal to L, there will be point F, B, and in this case value will be minus WL by 2. Now draw FD and BMD for this portion. Here is WL by 2 at point A, and here is minus WL by 2 at point B, and x की power 1, so it is analogous with the equation y equal to m into c. So there will be an inclined line, so we can make it this way. Close the curve. This is the shear force diagram. Now, when we are understanding, when we are discussing steps to draw SFD and BMD, they are sub case in second step. If there is shear force is being 0 for a given section, here is section given AB, and for this section shear force is being 0 at this point, then we are required to calculate this 0 shear force point. This is 0 shear force point. So we will calculate the position of 0 shear force point. So now position of 0 shear force point. This is general equation, and all these points lies on this equations. The value of x, we can found for this point, because here shear force is being 0, so we can write fx equal to 0. Why we are writing fx equal to 0? Because fx is located on y-axis and y-axis is being 0 at this point, so fx equal to 0. From the equation, WL by 2 minus WX equal to 0. So x equal to WL by x equal to L by 2. At x equal to L by 2, shear force is being 0. Now for the same section, we will calculate now bending moment. If we are moving from left to right, then first point is MA. MA equal to for this section, MA equal to for this section MA equal to WL by 2 into x minus W into x by 2. This term will create the problem. Now understand how it is coming. Wx is the total load. W into x is the total load, total weight of the UDL acting at the center of this length. The center of length x will be at x by 2. Here will be Wx, and it is at distance x by 2 from this section. So moment of Wx Newton about this section will be Wx into x by 2, and it is in downward direction, so considered as negative. For x equal to 0, in both terms there is x, MA will be 0. And it is already discussed, for start and end point of the beam, of the simply supported beam, bending moment is 0 until and unless an external moment is not given. And for x equal to L, there will be point B. This is also an end point, so bending moment about this point will be 0. Put the value of L and we will find the value 0. Because when we move from right to left, B will be the start point, so moment about B will be 0. So for both section, for both load point, bending moment value is 0. So when we will draw SFD or BMD for this section, BMD for this section, here at A value is 0, at B value is 0. But from general equation we are finding there is x ki power x, the power of x is 2. Power of x is 2. This is Wx into x by 2, it can be written as Wx square by 2, then power of x is 2. And it is analogous with the equation of parabola. So here will be a parabolic expression, but at both point value is 0. So When we are discussing S-step to SFD and BMD, at point point 3, there is a sub case. Whenever for a given section shear force is being 0, then we will locate the 0 SF point, and for this point we will calculate the maximum bending moment. Further in discussion, we will show you by a derivation at 0 SF point bending moment is maximum. So now we will calculate BM max. The BM max will be M is maximum at x equal to L by 2. To put this value into this equation, WL by 2, we are putting the x equal to L by 2 in this equation, right? We are putting the value of x equal to L by 2 in this equation, WL by 2 into L by 2 minus WL by 2 into L by 2 into 2. So value of M max will be WL square by 8. WL square by 4, here will be WL square by 8, or when we go for addition and subtraction, then it will be WL square by 8, right? Now we can draw SFD and draw BMD, because at A value is 0, at B value is 0, but at x equal to L by 2, bending moment, maximum bending moment value is WL square by 8. Variation is of parabolic nature, because there is the power of x is 2, so it can be drawn as this one. So this is the required bending moment diagram for this problem, right? In further, we will discuss problem number 4 in next lecture. Now we will discuss problem number 4. Draw SFD and BMD of simply supported beam subjected to UVL over its length, right? Loading diagram for this case is, there is simply supported beam AB of length L and UVL of maximum magnitude, maximum intensity line W Newton per meter is given, and for this case we will draw CF force diagram and bending moment diagram. Okay, follow the procedure. First we will calculate the reaction. For reaction we can draw FBD of this section, entire weight of UVL is the area of triangle, height is W Newton per meter, length is L, then total weight will be WL by 2, half into base L into height W, WL by 2, and will act 2/3 of length from 0 intensity line and 1/3 of length from maximum intensity line. When we apply sigma Fy equal to 0, there will be equation RA plus RB equal to WL by 2. This is equation number 1. For sigma MB equal to 0, it will be RA into L minus WL by 2 into L by 3 equal to 0, and will be, here L cancel out, RA equal to WL by 6. And similarly, when we will put the value of this RA into equation 1, RB will be WL by 2 minus WL by 6, and it will be W 6 WL minus 2 WL. This is 4 WL by 12, or it can be written as WL by 3. So reaction is now known. RB is WL by 3 and RA is WL by 6. Now, we will calculate shear force value. There are two load points A, B. So there will be one segment. Now we will consider the beam of length x, and this section will be just left of B. So we can draw the beam here at distance x. This is WL by 6. And see, intensity at this point is small w dash, small w dash at here. I am considering the section at here, and this is section x, and intensity at this point is small w dash, right? So major challenge is now is to calculate the total weight of this axis length of UVL, because maximum intensity line for this section is W dash. So how we will calculate the total weight of this UVL? So it will be discussed here in another page. So this is our beam, this is intensity, maximum intensity line W Newton per meter, here it is length L. Now we have considered section here, this is length x, and here is the intensity small w dash. Say this is A, B, and this point is C, and this point is C dash, and this point is B dash. The triangle AC dash B dash and triangle ACB, they both are similar one, and for this triangle tan theta value will be same. Tan theta will be same, right? So when tan theta will be same, then perpendicular base ratio will be same. So we can write C dash B dash upon AB dash equal to CB upon AB, right? C dash B dash is equal to W dash, AB dash is equal to X, CB is equal to W, and AB is equal to L. So we can find W dash equal to W upon L into X, right? This is the maximum intensity line for the section UVL, and unit is Newton per meter. When we calculate the total weight of this UVL, right? The total weight of this UVL is now, this beam is now, will be this UVL will be now like this one. Here the maximum intensity is given W dash equal to WL by X, Wx by L Newton per meter. Length of this beam is X, and total weight will be, when we draw the BD of this UVL, it will be like this one. Total weight is area of this triangle, then half into base is X, and height is W dash. W dash is equal to Wx by L, or we can write Wx square by 2L. So total weight of section UVL is always Wx square by 2L. Total weight of section UVL is always Wx square by 2L. You have to recite it. There is no need Each time in the given problem you go for this lengthy calculation, you just have to guess, you just have to put the value directly. The total weight of section UVL is Wx square upon 2L. Now, if section is at here, then you go for the calculation of bending moment. That means here is the section, right? Here is the total weight Wx square upon 2L, and this length will be x by 3 and this will be 2x by 3 in the BD, right? Yeah, here we can see it. This length will be x by 3 and this will be 2x by 3, right? When we will consider the moment of this total load about this section, this moment will be Wx square upon 2L into x by 3. Why I am telling you right now? Because this expression will be used when we will calculate the bending moment about this section. Bending moment about this section will be moment of this total load of section UVL about this section, Wx square upon 2L into x by 3. It will be of magnitude Wx cube upon 6L. In case of shear force analysis, you have to recite the section value of shear force for section UVL is Wx square by 2L, and value of bending moment for section UVL is Wx cube by 6L, right? So we will put the value directly during the analysis whenever they are required. So Fx equal to first WL by 6, then come there is the x length of UVL, and total weight of x length of UVL is W, total length of x length of UVL is W x square by 2L, already we discussed, and it will act in downward direction, so it is negative, so directly we will put it here Wx square upon 2L. Here there is the power of x is 2, so variation is of parabolic nature for CF force diagram, right? And for x equal to 0, there will be load point A and value is WL by 6 minus 0, that's WL by 6. For x equal to L, FB equal to WL by 6 minus WL square upon 2L. It will be equal to LL cancel out. It will be equal to minus 6 for WL by minus WL by 3, minus WL by 3, right? So draw. Now we are finding, we can go for the plotting of shear force diagram. At point A, value is WL by 6 and it is positive. I am showing it here. At point B, value is WL by 3. I am showing it here. And variation is of parabolic nature. So they see how we will draw it. It will be draw like this way. It will be draw like this way. Right? Again we are finding for the section AB, for this section AB, shear force is being 0. So we will calculate 0 shear force point. We will calculate 0 shear force point. So 0 shear force point for this section. Fx will be 0. say WL by 6 minus WX square upon 2L equal to 0, and W cancel out, and it will be this is 3, and this will be x equal to L by root 3. At x equal to L by root 3, shear force is being 0. Right? Now, we will calculate bending moment value for this section. I am plotting the same diagram. Sectional U will. Here intensity is W dash and below is W to X by L, and here is the value WL by 6 and sectional length is X. This is point A. Mx equal to, Mx means bending moment about this section. The bending moment about this section will be the moment of all vertical unbalanced forces about this section. First force is WL by 6. When we are moment of WL by 6 about this section is WL by 6 into X, right? It is positive because in the sign convention already we have discussed upward forces, bending moment of for upward forces, bending moment of upward forces for left segment is positive, right? Now, bending moment for this X length of UVL, or say sectional UVL, bending moment for section UVL already we have discussed it, the special case of section UVL. Here we find that it is always equal to Wx cube upon 6L. You have to recite it, keep it in your mind. Value of section UVL, right? Value of section UVL is always Wx cube upon 6L. Why it is negative? Because the total weight is in downward direction and bending moment of downward forces for left segment is negative. Now, A and B, they both are start point. So, we know MA equal to 0, for x equal to 0, MA will be 0, and for x equal to L, MB equal to 0. They both are a start point, there is no external moment given, right? So, bending moment for these points are 0. But we will calculate maximum bending moment because for this section AB, shear force is being 0 at x equal to L by root 3. So, bending moment maximum, that is M max at x equal to L by root 3. Put this value into this equation, WL by 6 into L by root 3 minus W upon 6L. L by root 3, it can be written as L is L cube upon 3 root 3, right? When we will solve it, we will find, the position of 0 as a point, position, the value of maximum BM for this point will be WL cube upon, let me tell you, we can calculate it, WL square upon 6 root 3, and it is minus WL square upon 18 6 into 3 root 3, right? So, this is maximum value. When you can solve it, WL square upon 6 root 3, take a common, here will be 1 minus 1 minus 1 upon 3, 3 when it will be 2 by 3 and 2 this is cancelled out, 3 3 3 root 3 and it will be equal to WL square upon 9 root 3. Check out this value, it is coming out or not. So this will be the expression. Again let me check it. WL square by root 6 root 3 is common, 1 minus 1 upon 3 is here, 3 1 minus 3 minus 1 2 by 3 and 2 3 3 3 is 9. So value is WL square upon 9 root 3, right. So bending moment value is maximum at x equal to L by root 3 where shear force is being 0. So draw it. For A, shear force is being 0, for A, bending moment is being 0, and for B, bending moment is being 0, and at this point, bending moment is W L square upon 9 root 3. Variation, here is power of x is 3, so variation will be of cubic nature, so it will be drawn like this way. So this is bending moment diagram of your wheel and this is shear force diagram.